Yeah, uh, good evening. So, welcome you all to the second online session for the doubt solving of this NPTEL course, Production Technology Theory and Practice. And the course tutor for this particular course is Professor Rona Kumar Chaudhary from IIT Kanpur, and I am Arnab, and I'm being assigned the TA duty for this particular course. So I hope that you have gone through previous week's lecture. So based on that, I have compiled a few questions, both from assignments, and we shall extend our discussion up to like beyond the assignment questions also. You can come up with your doubts pertaining to last week's lecture only. Okay, so coming to the first question, and yes, I expect this session to be a bit interactive so that you also participate in this discussion. Yeah, am I clear? Like, is my voice clear? Is my voice audible? You can unmute yourself and tell.
Yes, sir.
Ashutosh? Okay, thank you. So, as you can see, the first question, carbon percentage in cast iron, it's a pretty straightforward question. So, what will be the correct answer? Like, among the four options A, B, C, D? Carbon percent in cast iron is less than that of mild steel. That's the first statement. Second statement is 3 to 4%. Third statement less than 2%. Fourth is more than that of mild steel. Fifth, more than 4%. Sixth is 1 to 2%. So you can see an incomplete iron carbon diagram on the right hand side. So I'm talking about this diagram. So from what percentage of carbon, like what will be the range of carbon percent for cast iron, and the same for steel? Like what will be the percentage range? Anyone? It's a basic question from material science, so I'm expecting an answer from your end. What is the percentage of carbon for steel? Like the range of carbon percentage, and for cast iron, what are the ranges? Anyone?
Sir, cast iron contain 2% of carbon.
Cast iron contains 2% of carbon. No, it's not correct. Like it's
More than 2%.
more than 2%, right? So yeah, so more than 2% still it's incomplete. Like till 6.67%, because if we go beyond that, like the material will become brittle and not applicable for the common engineering applications. Although its strength will increase, but it will become too brittle to be used in day-to-day engineering applications. Okay, so so what will be the correct answer among A, B, C, D? It's less than that of mild steel. No, it's 3 to 4%. Yeah, that's correct. Like it comes within the ascertained range. It is less than 2%. No, more than that of mild steel. Yes. So 2, 4, C is the correct option. Right? Do you have a different answer? I think C is the correct option. Yeah. So see, let us revisit this iron carbon diagram. So I have designated this numerics here, 1, 2, 3, 4, like that. You have to identify the phases that are being shown by these numbers. So what does this phase 1 indicate here? Yeah, anyone? What is the particular phase? I have marked in blue. Ashutosh? Okay, Kushi, can you say what is the phase that has been designated by 1? This one? It's delta iron, right? It's the delta phase of iron. So this line represents 100% iron. So from 0 to 910 degrees Celsius, iron exhibits a particular phase which is called alpha phase. So this 5 is basically alpha phase. What is this nature called? This exhibiting different crystal structures or different properties at different ranges of temperature. What is this called in general? We have a metallurgical terminology related to it. It is called allotropy, right? So from 0 to 910 we have alpha phase. So that's this number 5 here, alpha ferrite. And then from 910 to 1395 we have the gamma phase. And from 1395 to around 1538 we have this delta phase, which is this one delta. Now if we slowly keep on adding carbon to it, then what we see that this particular temperature at which we will be attaining this particular phase, that changes. Like as we are increasing carbon in this direction, as we are moving, we see that the temperature at which we can experience the transition from alpha to this gamma phase, it's changing. And moreover, we will see that there is no like single temperature at which this change or transformation is occurring. Rather, a transition zone has been formed in between. So this red colored region that I am marking here, that is the transition zone. So what is the composition of the what is the phase composition of the transition zone here? This is alpha, this is gamma, and this particular part is delta. Then what is this part? This is alpha plus gamma, right? Am I clear, or just tell me if,
Yes, sir.
yeah, it's basic, right? So similarly, here we have liquid phase above this particular line. So this number 2 is nothing but delta plus liquid. Similarly, this number 6 is delta plus gamma, right? Okay, so a few more points are there. I'm coming to them slowly, one by one. So what about this point? What is so special about this point and this point? And they are being designated a particular name, and even this composition has been, this particular composition of iron or steel has been named after this point. So what is this point? What is the name of this point? You can unmute yourself and tell what is the name of this particular point. This is eutectic, right? Or is it eutectoid? This eutectic point. Eutectic point is characterized by a transition of phase from a liquid to solid. So what are the solid phases here? What are the solid phases here? So this particular line in magenta, it's actually cementite, Fe3C, and on this side, like on the left hand of this side, we have gamma. So this portion, it's nothing but gamma plus cementite. So do we have a particular name assigned to this phase composition? Have you heard about ledeburite? Have you heard
No,
about?
sir.
Okay, so it's basically like 4.3 percentage of carbon in iron, and that is the elemental composition. And if we talk about the phase composition, then it's gamma plus Fe3C. Okay, so this particular composition, it's called ledeburite, and the transition from liquid phase to this ledeburite phase, or to be more specific, gamma plus Fe3C, that is being called as eutectic point. This is that point. Okay, and this is the elemental composition. Similarly, if we talk about this point 11, so what will be that? It's nothing but ledeburite plus, so I am denoting ledeburite by Ld. Okay, this is Ld, ledeburite plus cementite. Or if we go deeper into the microstructure, which I will discuss after some time, we will see that this particular cementite is formed at the grain boundaries. Okay, so we call that. So this is Fe3C plus ledeburite, and this part is what will be 12. What will be the phase composition of 12? It's perlite plus ledeburite, right? Coming to this point, so this point is more familiar to us because we have seen that most of the manufacturing processes related to the steel industry are being carried out with respect to these two lines, these two or three lines, and the intersection of these lines is this particular point. So what is the name of this point? It's eutectoid point, right? And this particular steel composition is known as eutectoid steel. If we go towards the left, it is called hypoeutectoid steel. If we go towards the right, it's called hypereutectoid steel. So if we talk in terms of phase composition, then it's eutectoid. Sorry, it's not eutectoid. Actually, the phase that is formed there, it is called perlite phase. So perlite phase is nothing but alpha plus Fe3C. Ledeburite was gamma plus Fe3C. Perlite is alpha plus Fe3C. So it is denoted by an elemental composition of 0.76% of carbon in iron matrix. Am I clear here?
Yes, sir.
Okay. So if we go towards the left of this line, so this is the composition of this particular line. Okay. If we go towards the left, we will see that the crystal structure will be somewhat like this. So perlite is generally, if you can see, observe under a metallurgical microscope, you will see this type of patches, dark and white patches. So this dark color represents Fe3C, and this white color is alpha. So it will come like this. These are grains, and this is perlite phase. Okay. If we come towards the left of this particular line, towards 14, then we will see that at the grain boundaries, we will find alpha phase. Okay. Alpha will be forming at the grain boundaries, and this alpha has been deposited before before this perlite phase has actually grown into this grains. So that's why we call it pro-eutectoid. It has happened before the eutectoid, before this eutectoid. So we call it pro-eutectoid alpha. Similarly, if we go towards point number 13, then what will be that, this grain, inside the grain, it will be perlite. What will be the grain boundaries occupied by? What will be the phase that will be occupying this grain boundary? It is nothing but pro-eutectoid cementite, right? Just as we are coming towards alpha phase here, there we are going towards cementite phase. So here, somewhere here we will get perlite plus cementite here, over here. So as we are going to this particular region, along with this perlite, we have this pro-eutectoid cementite. Just in place of alpha, we will have pro-eutectoid cementite deposited at the grain boundaries. So this is just like a deeper understanding of what you have read in your UG level of metallurgy pertaining to iron carbon diagram. So do you have any other doubts regarding this iron carbon diagram? Then we can clarify that here only. Hello?
No, sir, no doubts.
Okay, okay. Then moving on to the next slide, the next question. So cast iron is used for lathe bed primarily because why is it being used as a material for manufacturing lathe bed? What is the bed basically? What is the purpose of bed in lathe machine? What is the purpose of lathe bed?
Sir, it provides foundation to the lathe.
Yeah, it's partially correct. Actually, yeah, it absorbs the vibration and the jerk that is being produced during machining, and also the due to the running of engine or the power source. So that vibration is partially being absorbed by this bed, and then it is being transformed to the foundation. Foundation is basically that cement or that what do you say, that protruded part over the ground on which we are mounting this lathe machine. So yeah, so what should be the criteria for choosing that particular material for this foundation? What should it be good at? Like what type of load is it being subjected to? So this is my machine, and suppose this is the bed that I am talking about, and below that I have say ground. Okay, so this is undergoing a vibrational motion, and at the same time this bed is being subjected to a dynamic compression loading, right? Is there any doubt here?
No, sir.
Okay, so it is a dynamic compression loading, and your material should be such that it has good fatigue strength in compression. Okay, so cast iron is good in compression, but it is very poor in tension. Why? Why so? Kushi, may I know, like, in which year are you are you studying now? Which year of BTech?
Sir, I'm in first year.
Okay, okay. So you're in mechanical engineering.
Yes, sir.
Okay, so you will encounter this particular subject in second year, I guess. So it's
Yes, sir.
better, yeah, it's better if you have an overall idea about this processes and also this material part. So the first week mostly deals with material properties, which is very important. Like uh, you will be facing a few problems after this slide. So those problems are crucial for the basic understanding of this subject. Anyway, so cast iron is used for lathe bed primarily because it is good in compression. Okay, it is very poor in tension. If you apply a tensile load, it will fail, right? And in case of compression, it will perform well. So that's why it is being chosen as a suitable material for lathe bed. So as the carbon content in steel increases, what happens? You are having a subject called material science, right? If I recollect properly. So what happens if we keep on adding carbon into steel? Its ductility increases or decreases? As the carbon percent increases, the ductility would reduce, because carbon induces brittleness to the steel basically. But at the same time, it increases the strength of the material. Why it increases the strength? Because it arrests the dislocation. So as the dislocation is traveling through the material, so what is dislocation? Basically, when we are applying load to a particular material, so you like macroscopically you won't be able to realize what is happening inside, but if you see that there are atoms arranged in different planes, right? So those planes are trying to slide against each other under the application of this particular load. So the most probable regions where this sliding will occur is generally called as slip planes. By the name, you can understand slip means that some slip will be occurring. So along that planes only, the atoms will glide over each other, or these planes of atom will glide over each other. So along that plane, if you put some interstitial carbon and you keep on adding that carbon, then what will happen? This particular interstitial carbon will arrest this gliding motion. It won't allow this slip to occur smoothly, and thereby it resists this deformation process. And hence, we can say that the strength of the material has increased. But at the same time, as we know that its ductility will also reduce. So, what is ductility? I hope you have come across this term by now, like in your first year itself. So, what is ductility? What is the definition? So it's the ability of the material to undergo plastic deformation. So this term plastic deformation is very important. Undergo plastic deformation without fracture. Okay. So if I have you come across this diagram? Is the stress versus strain curve?
Yes, sir.
Okay. So what is this stress? What is this stress? And what is this stress? This is called yield stress. This is called ultimate. In case of tension, we will write ultimate tensile stress. Since sigma and epsilon both are in positive direction, so we are considering this is stress versus strain curve in tension. So we are writing as UTS, ultimate tensile strength, and this is the point of fracture. So this is the from 0 to this particular, say, epsilon 1. This is elastic strain or elastic region, you can say this part, and from here to, say, this is epsilon f. I am denoting this fracture strain as epsilon f. This is the plastic strain, right? So the ability of, so larger this particular value is ef minus e1, more ductile your material is. Okay. In case of brittle materials like cast iron, if you subject it to tension, it will fail like this. Okay. It will attain a much higher value of sigma y, like it will be higher than sigma y. In that case, there's nothing as sigma y as such. This is that ultimate strength. But after this, there is no plastic region. The material will instantly fail. Right. So this is not a ductile material. This is a ductile material. So as carbon content increases in the steel, hardness is increased and ductility decreases. Okay. By the way, sorry, the term that they have used here, the property that they have used in the options is hardness. Strength also increases, but yeah, talking about hardness. What is hardness? Hardness is the resistance to scratch, right, or wear. So it is mostly a surface phenomenon. This is a bulk phenomenon strength. This is mostly a surface phenomenon, hardness. So if you increase the carbon content, the hardness will increase. Okay. Chromium in alloy steel improves what properties? It improves corrosion resistance. That's why you will find that in stainless steel we have added chromium, right? In cooking utensils, like the utensils which are used for cooking, then in surgical instruments you will find that stainless steel is used extensively. Okay. So stainless, why we use stainless steel? Because it is corrosion resistant. So your utensils are subjected to water and other fluids which will salt is there, like in your food you will find salt. So basically whichever items that will induce corrosion in the material, we want our material uh, like to be protected against those particular elements. So in cooking utensils we use stainless steel because we want it to be corrosion resistant. Similarly, in surgical instruments also, we don't want it to get rusted or get corroded, because like they are being used to perform different types of surgical procedures, operations and all. So we want a corrosion resistant material there. Second of all, strength. Yes, it increases the strength. Wear resistance. Yes, it increases wear resistance. So most of the options, like three options are correct. So you can say that yes, all of them. What is happening? Okay, so the next question. In fiber composites, ductility and toughness is provided by which material? Which, not material, I would say, what is composites and what is fiber composites rather? So, in fiber composites, what is happening? 1 second. Yeah, can you just unmute yourself and tell like what is the correct option here? In fiber composites, ductility and toughness is provided by which element? Matrix, fiber, both matrix and fiber, or resin? Yeah, what will be the answer here? So in fiber matrix composite, you have a matrix and you have fibers laid on top of it. So it can be in different orientations like this, or a combination of horizontal and vertical like that. So this is the top view. In like 3D view, you can see it's something like this. Okay. In between, you have another layer. So these are the fibers, and in between you have matrix. So what is the role of fibers? Anyone?
Fiber carries the load, sir.
Yes. So it is the reinforcing element. It carries load. Correct. And what is the like purpose of matrix? What does it do?
Matrix provides ductility and toughness.
Yeah, that's it. Like it hold first of all it holds the fibers into place. Otherwise, the fibers will get disintegrated or disoriented. Like this, it will become. Second of all, it provides ductility to the fibers. Like it accommodates the excess. You know, while loading, some deformation will be there. So the fiber shouldn't break, and that's why we are providing this matrix. Material that is unable to be deformed plastically without fracture is called a high strength material, high hardness material, ductile material, or brittle material.
Britain, what is it?
Yeah, basic question. So this term plastic is very important here because I had shown in that graph, right? There is an elastic region and there is a plastic region. So when you're removing the load in the elastic region, the material is recovering its energy, or rather, I would say the strain that it has undergone. So that particular strain is recoverable. But beyond that um elastic region, if you are loading the material into the plastic region, whereby if you are removing the load, that entire strain isn't getting removed. Rather, some amount of residual strain remains in the material. So if you want to observe it graphically, so say this is the elastic point, elastic region. Sorry, like this is the yield point. So if you are loading up to this point, anywhere, like it, you can load up to here, you can load up to here, you can load up to here. So loading and then unloading it, then ideally the material should follow this particular path, and this strain is getting recovered. This is the elastic strain. But say you load this material up to this point, okay, beyond the yield point into the plastic region, then what will happen? If you unload the material at this point, your material will follow a graph like this. Okay. So, so this was the total strain. This is the recovered strain, and this small part which didn't get recovered, it is called residual strain. Okay. Am I clear here? You can expect some basic numericals, right? I will discuss some numericals in the upcoming sessions. So you might be asked to find the ratio of this particular components, say the recovered strain and the residual strain for a given loading condition. So you can conveniently apply Hooke's law over here, approximating this to be a straight line, and the slope of this line is nothing but your Young's modulus, right? So if you know the value of stress up to which you are exerting, that you are exerting, up to which you are loading, then you can easily calculate, and for a particular material, you can easily calculate the value of ER, or sorry, epsilon R. That is the recovered strain, or you can also say elastic recovery. So it is nothing but what? Sigma by E. And from this particular graph, you know the value of total strain that the material has undergone. So this residual strain is nothing but total strain minus recovered strain. From here, you will get this term. And if you are knowing both these terms, then you can find one ratio, the ratio of the like how much residual strain is there to how much recovered strain you have achieved. So that ratio sometimes gives some additional information regarding the behavior of the material, mechanical behavior of the material. So one just question, just answer from your intuition. Suppose we are increasing the temperature, then what will happen? Suppose during this particular loading condition, this loading condition, say we are doing one exercise. First we are doing this at say room temperature, and second we are doing at an elevated temperature, say 500 degrees C, or maybe at 200 300 degrees C. Then what difference or what differences will you notice? What differences will you notice between these two particular loading conditions? Am I audible? Hello?
Yes, sir.
Okay, so you can just try. Yeah,
Uh,
Karthik.
with increase in temperature, Young's modulus decreases.
Increase in temperature, you are saying that Young's modulus decreases. So what is that phenomenon called?
Actually, not remembering the name of that, but
Creep, creep. It's called creep.
creep. Okay, okay.
So see, basically creep is not what that the decrease in Young's modulus is basically not creep. Rather, we would say that if we are subjecting a material to a constant load, say the load is not changing, but at an elevated temperature, we see that the material is getting strained. Okay. So see, from this particular graph, at a given strain, we will say that the stress value is this much. Say at this particular strain, the stress value is this much. Okay. But if we are doing the same experiment, say at an elevated temperature, then at this given stress, if you are loading the material, you will see that the material is straining by itself. Okay, so that phenomenon is called creep. Okay, so that's just a basic overview. So if you are like if you go through the courses which deal with this particular phenomenon, like material properties and all, then you will learn deeper about that. Okay. Maximum load experienced during the tensile strength, maximum load experienced during the tensile test divided by the original area is called yield strength, tensile strength, true stress, true strain. What will be your answer? It's tensile strength, right? Ultimate tensile strength.
Ultimate tensile strength.
Yeah. So how is it different from like first of all, there are two types of stresses that we generally like. We define stress in two different ways. One is engineering stress, and the other is true stress. So what is the difference between that?
In engineering stress, we consider initial original area, while calculating the true stress, we considering instantaneous area.
Hmm. So from which point, so from this graph you tell, from which point we may experience a bifurcation of the two curves for sigma engineering and sigma 2.
After proportional limit, elastic limit.
Yeah, generally after here, it goes like this. So you can see here that the value of true strain, true stress is greater than the value of engineering stress. But this is true in case of tensile test. In case of compression test, you will see the opposite thing. The engineering stress is greater than the true stress in this particular domain. Like this. So here no necking and all is happening in case of compression. So this sudden decrease part is not there. I hope like you're clear, like it is still clear here. And if you have gone through the lecture videos, you can also relate this particular thing, because there sir has actually derived the relation between sigma t and like what is this function actually. He has derived that. You can expect some numericals from this type of derivations or this type of formula. Increase in strength that occurs in metals when their strength is called which type, which phenomenon? Increase in strength that
Strain
occurs in
hardening.
yeah, strain hardening. So in this particular graph under tension, this is the strain hardening zone. Okay, and beyond this, after necking has started happening, it is called strain softening or necking. So with strain, the material becomes softer because some void has happened. Local voids are there. And due to these local voids, the cross-sectional area, which is actually, so if we take this cross-section here, you'll see that the actual area which is resisting the deformation has decreased suddenly by a large amount, and that's why the material starts snaking and then it fails. So can you tell me a practical application of this strain hardening, like in manufacturing industry, where you can visualize this particular phenomenon? I hope you have heard of this term rolling, forging, this type of operations.
Yes, sir. Yes, sir.
Yeah, so there the material is being subjected to a compressive load, and under sequential loading, if you're increasing the load, the material becomes stronger. Okay. So that's why the strength of the material also increases, and at the same time, the grains are also getting oriented in a particular direction. So you can say that the strength of the material increases in a particular direction. In the plastic region of the stress strain curve for a ductile material, which of the following options will be correct? So from here to here, Hooke's law is being followed, whereby we can write this particular expression: sigma is equal to, Young's modulus into strain from 1 to 2. From 2 to 3, what is the expression that we write? What is the expression? So this is the plastic region, right? Beyond
Equal
2.
to K epsilon to power n.
Mm-hmm.
Exponent
Yeah.
law. Your exponent law. Sigma is equal to K epsilon to power n.
Is it so?
Yes, sir.
See, there is a mistake here. The graph that I have drawn here is for engineering stress versus engineering strain. But this particular expression or formula, whatever you say, this law, It is valid for true stress versus true strain. So this is valid for this one, not this one. Okay. So you can write here sigma t is k into epsilon t to the power n. See, this part is common for both the cases, both engineering strain and engineering stress versus strain and true stress versus strain, because in this particular range, say from 1 to 2, I have exaggerated it, but actually this chain is very less. So some like naturally you will find the graph to be somewhere like this. And this part is so small that we can conveniently say that my true stress value is almost equal to engineering stress value. But beyond this yield point, as the cross section of the material is changing significantly, it is like changing the values of the stress, true stress. Again, you can expect some numericals from this particular expression. So yeah, I think this numerical was already discussed in one of the videos, lecture videos. So just doing a recap here. You have a material which is 60 millimeter long. It's a mild steel bar. It is being elongated thrice by 0.5 mm each time. Then what is the true strain that has been induced into the material? So how will you, what will be your approach for this particular problem?
Natural log of final length by initial length.
Yeah. See, this in this case, you know the relationship, like how this L is changing, right? So what I am trying to say is L initial to L final. This is the true strain. This is the expression for true strain, right? So in this case, you know that this L and this L is same. But suppose this L is some other function. It can be some other function, although it generally isn't. In that case, you should do this particular integration and find out, okay, what will be the value of true strain. But in this case, you can write here like sigma total, since it has happened thrice, so sigma epsilon total is equal to epsilon 1 plus epsilon 2 plus epsilon 3. So the first term, it's L1 to L2, L2 to L3, L3 to L4, and so on if there are multiple cycles. So here you are just plugging in the values, like dl by L is nothing but ln L, right? So for the first case, L1 is 60 and L2 is 60.5. Similarly, the next one, the limits are 60.5 to 61. For the third case, 61 to 61.5. If you substitute the values, you will get an answer around I think 0.0246, something like this. Okay, something of this, something within this range. So the main purpose was not just discussing this numerical. The main purpose was to say that suppose this L is not just a function that you are seeing here. Suppose it is some other function, L naught plus k of L to the power n, something like this. I am not arbitrarily mentioning it. In that case, you would have to perform this integration and find out this particular function. Here it's ln L, but in that case, you have to find out this particular function after carrying out this integration. Then plug in the values and you will get it. One common problem can be related to temperature. So with temperature, suppose you know the relationship between L and T. So from there, you can find out that with temperature how length is changing and what is the strength that is getting induced in the material. So that is a different scenario after all. Okay, another small thing. Yeah, see, you're using this formula to find out the true strain, right? There's another formula. Suppose you know the engineering strain. So from there also you can find out the true strain. What is that formula?
True strain is equal to natural log of 1 plus engineering strain.
Engineering strain, right? Suppose you know the value of engineering strain. From there also you can calculate the true strain value. But in this case, you don't know the actual value of engineering strain. So you might be asked to calculate engineering strain, and then say the stress at that particular point. All those things can be calculated. This can also be, this type of numerical can also be combined with this thing, this particular expression to find out the stress values, true stress values. So as you practice more such numericals, you will get a better understanding of the concept. So coming to the next question, plastic deformation in a metal occurs on planes that are farthest apart, that are of lowest atomic density, where the resistance to slip is minimum, where the atoms are densely packed, that are close, the planes that are closer to each other, that are orthogonal to each other. So as we know that if we take up a material, see, Rakesh, you're in which year now? Hello?
Already completed, sir, BTech.
Okay, okay. Yeah. So have you done this metallographic experiments whereby like you etched the samples and viewed it under the microscope to see how the grains are present? So did you do this type of experiments in your UG?
Yes, sir.
Okay. So see, most of the metallurgy people will be doing this. Say you have a material, you want to see the grain distribution, the like how the grains are distributed, what are the grain size, all these things. So they will polish it up to a mirror finish. So this involves multiple levels of polishing using polishing papers, and after that, diamond suspension, diamond paste, or some colloidal suspension. So you will get a mirror finish. Okay. So after that, you do etching. So different commercial etchants are available. Sometimes we use Kroll. Suppose for titanium we use Kroll's reagent. So like these different reagents are there. So this etching will remove the thin oxide layer on top of the material, and it will expose the grains and the grain boundaries. So more prominently it will expose the grain boundaries. Your material. So after polishing, you have removed the film, but after this etching, these boundaries will be visible because this etchant will do selective etching along these boundaries. Okay, more material will get etched away in this boundary since there are less material present there. So here you can see if you are viewing this under a microscope, you will see this type of structures. It can be a different form also. It can be like this. So it depends on the material and what type of treatment or pre-processing it has undergone. So these are the grains. Okay, what are grains? So grains are entities where the atoms are arranged in a particular fashion, in a particular order. It is an ordered arrangement of atoms. So say in this particular grain G1, the atoms are arranged in this manner in a FCC lattice structure. Okay. FCC crystal structure. In the adjacent one, here also the atoms are arranged in FCC, but they are arranged in a different direction, say in this direction. Here also you will find FCC, but they are arranged in this particular direction. Here they are arranged in this direction. So like this. So when these two particular grains are meeting, this is the boundary that is forming. Here I have atoms which are arranged in this particular direction, and here I have atoms which are arranged in this particular direction. So this is called a defect. Why defect? So grain boundaries are basically defects. Why we call it defect? Because why? Because it is stopping the arrangement, this particular ordered arrangement, right? So the atomic arrangement is changing along this particular boundary. So we are calling it a defect. So what is plastic deformation? So when this material, this particular material is loaded, then these atoms, they will tend to move along. So suppose this is one plane of atom, and this is another plane of atom. Okay. So due to this load, these atoms will try to glide over one another. These planes of atoms rather will try to glide over one another. This phenomenon is called slip. Okay. Slipping rather. So due to this slip, what happens? Okay, so this there are multiple regions where this slip might get arrested. Arrested means they are not able to proceed from one point to the next point. So what are those reasons? One, if you have any interstitial elements or phases, say in between you have some interstitial elements, so this is resisting the gliding motion. Second is this defects, or rather grain boundaries, I can say in this case. These are type of defect. There are other defects also. Even the surface, any surface of a material is also a defect, because your atomic arrangement is stopping at that point. Beyond this, in the air, you are not having any material. So your surface is also a defect. So grain boundaries, yeah. So at the grain boundaries also, this slip has to change its direction from, say, D1 to D2. Okay. So here also, the slip is getting arrested. So these are there are many other ways to arrest slip motion, but these are the two most common ones. So where does this slip most probably occurring? Right? In which planes the probability of this slip occurring is highest? The planes which are containing the largest number of atoms. So we generally define it by a term called planar density of atoms. So the plane which is containing more number of atoms in a given crystal structure is more prone to allow slip. Okay, slip motion. Yeah, this is one criteria. Second criteria is higher the distance between these two planes, which are more closely packed. There can be other planes also in between, but we know that slip is occurring in this plane. So these are the slip planes. So the higher the distance between these slip planes, more is the probability of the slip occurring. Okay. So the option 1 is correct here. Option 4 is correct, and also the planes where the resistance to slip. So I have already mentioned that these are the resistance to slip. So where the resistance to slip is minimum. Suppose we have less number of interstitial elements which are present in that plane. So there the plastic deformation occurs more pronounced, in a more pronounced manner, because slip is more pronounced there. So 1, 3, and 4 is the correct option here. Okay, this is the last question for today's session. So built up edges does not form at which of the following conditions, machining conditions to be more specific?
Higher cutting speed.
Yeah, at higher
Higher
cutting
cutting
speed.
speed.
Yeah, at higher cutting speed, you are not allowing the. This is my tool, my material, and the chip flow is happening in this manner. So if you have a very high cutting speed, you are actually reducing the interaction time between this particular chip and this tool, and also in this portion. So as you are reducing the time of interaction, the probability of the weldments that are occurring here, which is basically BUE or built up edge, the probability of that occurring also reduces. Okay, at higher cutting speed. So that's how you are reducing the chances of the occurrence of built up edges. Under what conditions built up edge occurs more prominently? You should be knowing, right, at what conditions it is happening in a more prominent or more pronounced way. Under what conditions? At lower and medium cutting velocity.
Speed will be small.
Yeah, what? Hello? Can you repeat your answer, please?
Ductile material having undergoing cutting operation having lower cutting speed. No lubrication is there in the operation during operation, and medium to low cutting speed, and feed is small. Also, also there is some reason that I'm not remembering.
Yes, and there are more chances of
Cutting
metallurgical.
length of the workpiece is more. That is also one of the reason. That is uncut thickness is more.
Uncut chip thickness. This one. Yeah, indirectly you're trying to say the depth of cut is more, right?
Yes.
Hmm. Okay, so like what happens is due to the metallurgical or the chemical affinity between the chip material and the tool material at higher temperatures, these atoms diffuse from one side, say from the tool side to the chip side. Okay, and some bonding is happening due to this weldment. Weldment is basically bonding between these two surfaces at different locations. So, what are the detrimental effects of this built-up edge? First of all, it it increases the this rake angle, right? Here, initially the rake
Starting
angle.
at
Uh-huh.
start increases the strength of the workpiece, but later on it decreases its life
Yes,
also.
right. So it also decreases the rake angle, right? Suppose after built-up edge, your tool will be like this. The like this is initially the tool looks like this. After built-up edge has formed, it will become somewhere here. So initially you are having a positive rake angle. Now you are having a negative rake angle, right? Initially you are having this one. Now you are having this one. So you're having a negative rake angle, so that increases the cutting forces, it increases power. Second of all, these built-up edges are not stable; they are breaking after some time, and due to that breakage, this force is also like sometimes it is increasing, sometimes it is decreasing. So there's a chatting motion or some dynamic load is being induced in the material, which is then detrimental to the surface properties of the workpiece and as well as the tool material. Third of all, sometimes we are adding certain alloying elements to the tool to improve its properties. machining properties, machining properties, strength, wear resistance, and all. So due to this built-up edge, the top surface is getting damaged, and hence the surface finish that you are actually getting in the workpiece after finishing here also built-up edge may occur. So this part is also getting disrupted or rather damaged. This surface finish is also getting tarnished. Okay, so these are the detrimental effects of BUE. Yeah, so that's it. So thank you. Do you have any other questions from your end?
Sir, can you show first four questions? I'll join later.
Okay, so in the first question, like it was a straightforward question, but as an extension, we also discussed a bit about iron carbon diagram. What are the different points? What are the phases that are here? Have you heard of pearlite? I hope you have, right? Pearlite is alpha plus cementite, right? So if you are asked that using lever rule, you find out the phase composition, like how much percentage of alpha is there, how much percentage of cementite is there in pearlite. Will you be able to do that? You know that this is the line which represents pearlite. You know the carbon percentage here. So this point also you know, and this point also you know. So this is basically Fe3C, 100% Fe3C. This point is 100% alpha. Here you have pearlite, which is alpha plus Fe3. So at these 3 points, you have the carbon percentage, right? 6.67, 0.76, and 0.022. So if you apply a lever rule here, I hope you know lever rule. So what will be that percentage of alpha? Yeah, Rakesh, if we apply the